All right. Hello everyone, my name's Alex and I'm doing my pre-completion seminar for my postdoctorate studies. The title of my thesis is Improving the Detection of Weed Species for Robotic Weed Control in Complex Rangeland Environments. Precision agriculture has revolutionized the cropping as we know it in a variety of different applications, from irrigation control to fertilizer application and of course to weed control. So what we have here is QUT's AgBot. It's been specifically designed for a cropping environment to navigate the cropping terrain and selectively apply herbicide or selectively apply mechanical means to remove weeds. Very impressive stuff. But this same innovations have not stemmed to the rangelands. What about our stock farmers who have cattle, sheep, massive expanses of land? We don't have the nice navigable terrain of crops. This is the terrain you have for the rangeland. It's a much more expansive. It's actually difficult to navigate. Those are tussocks that ATV is bouncing over. I've taken that drive myself and it's not very good for a robot. It's quite bumpy. That crop AgBot from earlier will not be able to work in this type of environment. But the weeds in this environment are very invasive and they're a problem. This is prickly acacia out on the Brody farm in McKinley. They are spraying it with herbicide. So for a robot to do this type of work, it's going to be quite difficult. Rangeland weeds, they invade ecosystems like we've just seen. Once they take hold of the land, they can endanger native flora and fauna and actually devalue the land and make it more difficult for the stock to muster and all sorts of problems. As a result, land managers spend billions of dollars controlling it. And there's some cost of lost production due to death of cattle or just inability to muster the cattle and losing your land mass, basically. So it's been ranked the #1 land management problem by Australian farmers. So the big picture solution that we envision for this project, it's basically a 4-step process that started way back in 2015. My contribution of this, my PhD, has centered on doing a proof of concept robotic spraying system, and that later became a manned prototype spraying system. In the future, we would have some of these robots driving around the paddock itself and spraying weeds, but that's future work. So my contributions to this solution have focused on developing a proof of concept trailer and growing that into an ATV spot sprayer. We actually had funding from Yamaha and the Australian government to facilitate this project. The research gaps that I'm specifically addressing are that there is no robotization of weed control in the rangelands. We're going to do the first solution for that. There are no existing in situ weed species datasets. So if there's no focus on the rangeland, how can we actually deploy any detection models without first collecting a very big data set of these important weed species? The rangeland environment presents a unique challenge that hasn't been solved in research. Have a look at some of these images. The lighting variation is crazy. The targets are at different lengths from the camera. The focus is in and out of focus for a robot to be able to see. Occlusion, grass, everything blocking the targets you want to identify. So it's a difficult problem that hasn't yet been solved with image analysis. Also, another problem that presents in our robotic solution is the problem of a real-time requirement. This is an image frame. If a robot is moving at 10 kilometers per hour, which is what an ideal spot sprayer would work at, the image frame is 280 millimeters in size, so we can only process one image at a time. Before we move on to the next image, we have to have that first one done. As a result, we only have 100 milliseconds to be able to detect in one image. So this is a very strict time requirement that we might not be able to satisfy. I'm not sure, it's a research gap. So fortunately, I did solve that. That's part of the PhD. My contributions, so what have I done? First robotic weed control solution. The first large multi-class weed species data set was introduced. I achieved 96% classification accuracy on that data set, and I achieved real-time throughput with complex CNNs. So let's go through each one of those outputs in excruciating detail. So it's a 4-step project overview that I've been working on since 2015 when I started the course. That's almost 4 years to date. So the very first thing that I focused on was a site-specific study. We looked at lantana in one single environment, and we asked ourselves, can we detect this lantana in situ and fast enough? One method that I proposed to be able to do this was to use leaf texture as a sole discriminator, because that would be very fast. We wouldn't have to employ a complex CNN. We could actually do it quick and fast if texture is good enough. And then we ask ourselves, is it time and cost feasible? So there's also worth mentioning there are spectral methods to be able to detect weeds. We've chosen to focus on image analysis methods because the imaging is much more affordable, easier to attain, and the spectral signatures are a bit more complex to process on the fly. So for this site-specific study, I looked at Lantana Camara in Hidden Valley, Paluma. We collected at the time what we thought was a big data set, 337 images. We had 83 images of lantana and 250 images of non-lantana. At the time we thought that was big. We've later found out that that's not big enough. But that served as a good test case for us. The texture descriptor that I chose to implement on this data set is basically this workflow in image analysis. We start with the input image. We go on to balance the shadows and highlights. Then we move to extract green from the image. Then we use a morphological open and closing to extract broad-shaped leaves. From that, we can take our leaf material in small texture windows and analyze the actual texture of every single window to see if we can tell a lantana is different from neighboring wildlife, plant life. In order to actually determine, quantify the texture of those windows, we utilize histograms of oriented gradients, a very traditional, well-used technique in image analysis over the years. Image texture can be described by gradient intensity, is basically how these things work. And you get a map that looks kind of like this. The edges of the target you're looking at kind of become more pronounced. However, one little research outcome of this is that histograms of oriented gradients aren't naturally rotation invariant or scale invariant, meaning they can't detect multiple targets of different sizes or if the target is rotated. In order to make it work, I had to use dominant rotation alignment and multi-scale histogram fusion to make them achievable for this task. I then employed my own machine learning classification strategy, which was 2 steps. The first step is a window that we've found from a lantana leaf or from something else. That's stage 1. Stage 2, a second machine learning model was employed to ask then, how many texture windows do I have in an image to consider it a target? So this was a 2-stage machine learning framework that we tested, and we got some good results. This is the system working on a test set. We have the raw photos, the light being balanced, extracting green, broad-shaped leaves, and then our target images with red drawn around the outside. The results were quite good. We got 86% average classification accuracy. So that's actually a good number for our data set because it was quite challenging. As I mentioned before, the light conditions, all this stuff, 86% is a good result. And it's very good considering the small size of our feature set. Single texture extractor is much easier to compute than a big complicated neural network. So it was fast and it worked. We could then put it on our robot. That's some more results basically of how well it achieved some stats. So we were then able to put the detection model on the back of our proof of concept robot, which is basically just a trailer that Peter Ridd had lying around. And we were able to mount 8 cameras on it. We mounted 8 sprayers at the back, and we used just a core i7 laptop to do all of our processing. Because the texture was so small, we were able to do it all with an i7 laptop, which is quite impressive. Here's a demonstration of it actually running. So on the left, we have vision of an actual spray on lantana, and on the right, you can see what the robot is thinking as it's moving through the field. So this is actually showing failure on the right. If you have a close look at our motion graph, the vehicle works in a straight line, it remains accurate, but as soon as we start to turn, it loses its motion accuracy. The reason for this, we were using very simplified motion sensing equipment. We simply had a wheel speed sensor and magnetometer for direction. And over time, as soon as it turned, the vehicle would think it's drifting off course. So we hit some limitations of our motion equipment for this cheap proof of concept robot. But the good thing about this is we learned how we can build our prototype to actually solve this problem for real. The work that I did in this case study was published to a conference in 2015, and we were awarded a nice prize, which was cool. Our contributions were correctly identifying lantana, leaf texture worked for lantana, and our low-cost prototype worked in straight lines, but it failed whenever we had to make a turn. The unfortunate thing here is I tried that texture descriptor on multiclass weed species datasets, and it actually didn't work. Now that kind of makes sense because you're going to find a lot of different weeds that have a similar texture, but they may have a different outer structure. So this simplified approach worked for one case study, but it's not applicable to all case studies, unfortunately. So we've learned how, throughout this time, to build a robotic solution. So moving forward, the next part of my thesis was to collect a very large data set so that we could have a method that worked in a variety of rangeland environments, not just our one specific environment. To facilitate this, we were funded by the government to be able to go out for 6 months and collect a hell of a lot of images. Our goals for data set collection, we didn't want to just go out and start taking photos. We actually thought about it and came up with a good plan. Target weed species of interest in our local region, collect images exactly as they will appear on the target robot. So in my previous data set, we took pictures with different phones, different cameras. There was no consistency in the data set collection. For this data set, the exact cameras, the exact optical system, lens format, everything is identical to what the target robot has seen. So the detection methods will work. We also made a goal quantifiably to collect 1,000 images of each species and then to collect a one-to-one split of positive and negative images from each location. So that's give it enough negative examples so the detection model can, find the positives. In order to facilitate this process, I developed a weed logger instrument. So it's a data logging instrument that allowed us to take photos, automatically label them in the field, and actually produce images that were already in a dataset format. So it accomplished a couple of goals for us. The first one, we could get the exact height, lens, everything to match the robot. That was done. We ensured consistent image acquisition, and we also accelerated the image collection process. So we could just get it done a lot faster because we had 3 of these instruments. The weeds that we chose to isolate, based on talking to farmers and NRM groups all throughout Queensland in the construction of our grant to fund this project, we decided to look at shiny apple, lantana from our case study, Parkinsonia, Parthenium, prickly acacia, which is out west that we saw spraying earlier, rubber vine, Siam weed, snakeweed, and most importantly, this negative class. So this isn't a weed class. It is the class of all other plant life or dirt or anything in the background. We throw it into the negative data set. So it's an important learning problem that we've established by making this class. We collected sites all across Queensland, from Black River, Paluma, Harvey's Range, Charters Towers, Douglas, the far reaches of Douglas, Cluden, Kelso, and McKinley. This took about 6 to 12 months with some help from our workers at the lab to go and collect all these images. This is the result. A lot of numbers here. The main one you want to look at is in the bottom right. We have 17,509 images total. And we also achieved our goal earlier of 1,000 images of each species. And importantly, we achieved our one-to-one split at each location site. So we've established a data set that we feel will be able to represent the rangelands quite well. So after collecting this data set, now we can get our hands dirty actually developing a deep learning model. The problem with deep learning is you need a data set that's large enough and labeled to be able to take advantage of its ability to learn and solve the problem. So we feel we've made a data set that will be able to use deep learning, and that's what we moved on to do. We set 2 goals. The first goal, can we accurately classify this data set to 90% accuracy? The second goal, can we meet our 100 millisecond time requirement so that our robot can actually have some success? We decided to employ convolutional neural networks, the latest and greatest thing in image analysis. A CNN is a great tool because it basically automatically learns and extracts features from images that you give it. All you have to do is get a data set that has labels, information for which class is which, feed it to the CNN, and it will use its series of convolutional filters to quantify those features and optimize it and make until it actually detects the classes that you're looking for. It requires very large data sets though. So our data set is 17,000 images. You'd actually want on the order of 100,000 or 1,000,000. So our data set, while being quite large, still isn't ideal for deep learning. So we have to use one other tool, which is called transfer learning. Transfer learning allows us to adapt a pre-trained model on a very large data set and then tailor it to your smaller data set. And you can actually get really good results because a pre-trained model has learned general image features that are still applicable to your data set. I chose to look at 3 different network architectures, BGG16, Inception v3, and ResNet 50. All of these are very high-performing networks that have won a variety of competitions over the years. They're also all available in Keras and TensorFlow and TensorRT, which is the libraries I'm using on my robot and for my analysis. One other important step to prevent overfitting to my data set, we could use image pre-processing techniques. So our data set of 17,000 images were taken, basically they're static. We can make it look like a larger data set by randomly augmenting those images so that it looks like they're in different rotations, they have different illuminations, and we're basically preventing it from overfitting to one type of image. We did this by rotating, scaling, shifting the pixel intensity, flipping the images randomly, lots of pre-processing techniques that allowed us to prevent overfitting of the models. Then we could actually start the training process. So for a bit of reference, it took 13.5 hours to train one model on a GPU 1080 Ti NVIDIA that we have. And basically, here's our plots. So the top 3 lines are the training accuracy. So our data set was split into a training data set and a validation data set. The bottom 3 lines is our accuracy on that validation subset. So as you would expect, we're optimizing on our training data set, so the results are going to be better. That's why they're a bit higher. The validation accuracy is what you really want to look at, and we're plateauing at about 95%, which is a very strong result. The main thing you want to see here are the small circles. They represent an individual model, one single model that is the best. And I pull that model out, and then I can deploy that in the field and see how accurate it is. So we took out the best VGG16 model, the best ResNet model, and the best Inception model. And it turns out ResNet was the best. At 95.7% accuracy, it outperformed the other 2. And we met our 90% classification accuracy goal. How about each species? How well are we detecting each individual species? Does it compare well to our past 86% on lantana? So shiny apple, that looks to be the worst, most difficult weed to classify at around 85%. Also snakeweed is around 85%. So interestingly enough, they quite look similar, and we'll have a look at that in a moment. So that may be a reason why they weren't doing as well. Lantana is up towards 90%. One model takes it to 92%, and that compares to our previous method, which was about 86%. So these are strong results. Another very nice result is our negative class. It is the best predicted class out of every one, and that's a very good result because it's such a complex class with lots of different wildlife in it. To get an understanding of which species are being confused for which other species, we can look at the best confusion matrix for our ResNet model. The one thing I want to look at here is that 0.04. So that is 4% of snakeweed being confused with shiny apple. So this confirms what I reasoned a bit earlier, is that shiny apple and snakeweed look a hell of a lot similar, and that's a reason why they're being confused. So if we can't expect a human to be able to tell the difference, it's okay to have the robot making 4% of that problem. There's nothing we can do about that. Similarly for prickly acacia and Parkinsonia, but our confusion levels are quite low, so this is good. Another interesting result, we were 98% right in predicting negatives. That means there were 2% wrong. So 2% of our negative class we thought were positives, false positives. Interestingly enough, because there are so many different species in our negative class, it just so happens that there's a species that looks like every single one of our targets. So, looking through every image, we found one that looked exactly like shiny apple, and the model predicted it was shiny apple. Similarly for lantana, every single weed had one in the negative class that looked exactly like it, and that just speaks to the massive variation in our rangeland. So ultimately, any model we train on any data set, when we go out into the real world, we're going to see some stuff that we haven't seen before. So that's an interesting outcome. So the classification accuracy was great, but how fast can we actually process these CNNs? So we moved toward our robotic implementation. Can we achieve real-time performance? I analyzed 3 hardware architectures. An NVIDIA 1080 Ti GPU, so that's something that's in a desktop. We're not going to be able to put that on a robot. I just wanted to see how well it compared to our robotic solutions, which are the NVIDIA Jetson TX2 in the middle, and the latest and greatest NVIDIA Jetson Xavier, which we also bought and were able to run some analysis on. So the inferences, the metrics I wanted to look at were inference time, how long does it actually take to process these images, and the power consumption of each device. Here are our results. The GPU, as you would expect, just powers through with a very fast inference time. However, it also has a massive power draw, and that's why it would not be feasible on a robot. I don't know how you're going to power that thing out in the field. So our robotic solutions, this is a bit more what we want. You can see our 100 millisecond time has been met, where all solutions are within our 100 millisecond real-time requirement, which is great. But the Xavier, it was actually marketed to achieve 20 times the performance of a TX2. We found for our application it's only twice as good, but it's close to 20, I guess, in some way. So that's the summary of our deep learning approach that I've implemented in my thesis. We got basically one paper published to scientific reports that included the data set and our classification methods. We've also got a paper under peer review looking to use these Jetson methods against some FPGA binarized methods. So that's a cool paper as well. Contributions, deep weeds data set, accuracy, speed, limitations. We haven't yet tested these results in the field. Again, we've only tested them on our data set. How are they going to hold up in the field? That's what our next part is about. Prototype development, so the final chapter of my thesis. Do our detection models hold up in the field? Is automatic spot spraying feasible? And does our robotic prototype outperform a human? So this is the proposed system. It started as a concept in Peter Ridd's mind, and it's now become a full-fledged weed control terminator. It consists of high-resolution cameras at the front, 4 of them, 5 sprayers at the back. We've developed our own electronics to interface with all of these sensors. And our main control board is at the front with 2 batteries to power the system, an advanced navigation GPS unit, and lots of other cool stuff. The contribution of others, I have to acknowledge, because this has been a project that has undergone a couple of different engineering theses. The target tracking and positioning system was overlooked by Jake, the spraying system by Brendan, mounting and construction of the prototype by Jake and Billy, and dataset collection and curation by Jamie, Ben, and Wes Banks. So, my contribution, I'll just mention, I oversaw basically all of these projects to ensure that our robotic system was being, going in the right direction. My contributions, I'll get into my detail there. I've developed the processing unit software, and I got to choose the processing units we want to implement. I chose to use 2 NVIDIA Jetson TX2 compute modules. I've nicknamed one of them Astro Jetson, which is the worker dog. It performs positioning and tracking, the image acquisition from our cameras, and controlling the sprayers. The other Jetson is Elroy. Now it's doing the hard stuff. The boy genius is doing deep learning inference engine stuff. So we've got one Jetson doing all of the deep learning, the other Jetson doing all the heavy lifting. We've also decided to use the robotic operating system. So this is a really cool tool that is an open source library for controlling robots. It allows us to, without reinventing the wheel, use positioning algorithms that are quite complex, and they're just something we can interface with nice and easily. It also allows us a communication framework so that Elroy and Astro can talk effectively. An overview of the software. I won't get too much into this, but there was a lot of development in actually crafting a software program to do all of the different things, interface with the cameras, interface with the sprayers, and we used the publisher-subscriber framework to be able to achieve this in C++. I also designed with a lot of care the optical system that we were utilizing. I did this way back when we had our weed logger tripods, basically. So that is setting what the depth of field will be from the ground. We've set that to about 30 centimeters so that the weeds are always in focus. We've also made sure that we have a shutter speed that doesn't blur when the robot is moving. And we've achieved 4 pixel per millimeter resolution, which is quite required to be able to detect those features. We also have a vision system. So previously, our robotic goal of 100 milliseconds was for 1 camera. On our robot, we have 4 cameras. So right there, we've quartered our goal. We've made it 4 times as hard for ourselves. We now have to process each image 25 milliseconds at a time. The solution? Why don't we process these inputs, 4 images from the cameras, in one batch on the GPU, so we can make it parallel. And it just turns out, fortunately, that it processes 4 images in 71 milliseconds. So we're still within our goal. So that's great. So we've got the robot, we've got the detection model. Let's start spraying some weeds, right? So I went out there with a deep weeds trained model. 8 different species in our trained model, and tried to spray shiny apple, just one of those weeds. It really didn't work the first time. The reason for that is because it was picking up Parkinsonia from West McKinley in an area where there's only shiny apple. So we were kind of making it a bit difficult for our robot. So one final step was to only grab shiny apple and negatives, and then retrain our model site-specific before we deploy it in the field. So that confusion matrix on the right is a retrained ResNet to shiny apple, and it's 81% correct on shiny apple, 97% on negatives, and we're ready to go for the field.
Yep.
That's the field results. That's Brendan driving. This is out near the Cowboys Stadium where I found some shiny apple on a grass background. You can see the shiny apple when it's identified with green squares right there, and it's sprayed as soon as it goes red. So this is live information that's extracted from the robot. We actually have a Z-axis as well, but I've just simplified the animation. This is a really easy trial site. There's shiny apple and grass. So this is our best possible case. And as you can see, it's hitting every single target, and there is no off-target spray. So this is a really good result. Just to prove that I'm not making it up, the graph stops as the guy's driving as well. Yeah, it's real. But yeah, this was a great result to see it actually, after years of work, finally in the field doing its job. It was great. I think you can see Peter tagging along there as well. So that was really good. So let's quantify that performance a little bit. We did 2 trials at this site with full quantification of the results. They're visualized on the left. Now there are 2 ways that we can analyze the performance. How is the detection model performing? Which is every time we take an image, how well did it detect our targets? It's actually different from how well were we spraying our targets, because we're collecting images at 20 frames per second. One target could be seen 20 times. So we could be 50% accurate in our detection and still 100% accurate in our spraying. So this is a nice problem for us that makes it a little bit easier for us to actually spray these targets. Fortunately, in this easy test trial, our detection was 97% for precision. So that's when it says I have a positive target, it's 97% right. And I couldn't analyze all 7,000 images because I don't have that much time. So I looked at 2 different cases. Of all the negative predictions, I looked at the highest confidence negative predictions and the lowest confidence negative predictions, i.e. the best and worst cases. And it just so happens that it was 100% right on the best case, and on the worst case, 95% right. So that's a pretty strong result. In terms of spraying, basically just visible quantification of performance, we had 7 targets, all 7 were sprayed, and we didn't spray anything that wasn't a target. So this is 100% accuracy, so that was great. Trial site 2, a little bit more of a challenge. So there's a few other weeds here that aren't in our data set, and it's a brand new location that we haven't seen before. So it's a lot more difficult a detecting problem. But it's still doing quite well. Unfortunately, we weren't able to ground truth the locations of our targets. I'm still doing that in some of the trials I'm conducting. So the performance I'm quantifying here is purely visible. I'm just looking to see if targets are being sprayed. As soon as you see a green, you will see a shiny apple come out the back of the vehicle. That's sort of it. You can also hear the solenoid clicking to identify a spray. So the performance of this was every target was hit. However, there was a lot more false positive sprays. It was finding weeds that weren't shiny apple and spraying them. So this is the quantification of that performance. It's not yet finished because there's a lot of data that I'm still crunching, but I was able to analyze the positive detections of this data set. Yes. So of the positive images, we're down to about 70% precision in the detection problem. But as I said before, there's a lot more images than there are targets, so our target performance was very good. Qualitative analysis, all the targets were hit, but there were a lot more false positives. So I had a look at those false positives, and we're actually finding weeds that we've never seen before. So it turns out that we're still spraying stuff that probably should be sprayed, so it may not be too big of a problem. So in conclusion, for this chapter, I plan to publish this work to Precision Agriculture, focused on our auto-weed system. The contributions: we had a successful development of a robotic prototype, and the detection system was validated in the field. Some limitations: well, the natural variability of our target scene is a very difficult problem. No matter how many data sets we collect, we're never going to be able to capture that full variability unless we just extrapolate with time. So the solution then is to, every time we take the robot out, save the images, put them back into the learning model, and it will just get better and better with time. So that's a problem that time will solve. So in conclusion, for the entire PhD, we've developed the first robotic weed control solution. We introduced a very large multi-class data set, we achieved our accuracy requirements and we achieved our real-time requirements as well. I'd like to talk about some future work that could stem off of this. In terms of detection, as I mentioned, continue to build the data set and improve the learning performance. For the robotics, it would be nice to localize the position with cheaper electronics because we're using a $12,000 GPS unit. For the farmers, we'd want to get that cost down so that we could actually have more industry engagement. And we think it could be achieved quite easily with a bit of work. We'd also like to automate the operation of the robot so it drives itself around. We've been making progress to that effect. And in terms of industry, we have a retrofitting service that we've basically put onto a Yamaha Grizzly. We should be able to replicate this for farmers, and we've got an interest from a few farmers. So there's a bit of a caveat here to chase up, I believe. Cool, that's it. These are my publications. Thank you very much for listening.